So I realized that I'm going to be a little bit off topic. So if what I'm talking about sounds very weird, just ask me lots of questions. I'm happy to try and elaborate, and it doesn't matter if I don't go through all the content. So this work is a program that I am pursuing with a brilliant set of friends and collaborators and various students in various combinations, appearing in some papers that is already out and some papers that will appear eventually in the coming months. So just to give you a little bit the context of where we talking about, my talk is about infrared dualities. So this is a very interesting physical phenomenon so that relates different systems that they look very different when you look at them small scales, but become the same system when you are at large scale. So think about boiling water and spin system, Ising model in 3 dimensions. So systems look completely different. At large scales, they are the same at small scale, they are the same at large scale, so in the infrared. And in the context of gauge theories, we know the very first example of systems that are related by infrared duality thanks to the work of Seiberg. So in the mid-90s, Seiberg put forward a proposal for a infrared dual description for the familiar supersymmetric QCD. So we're talking about a theory which is SUNC with NF flavors, which in a particular range of flavors in the so-called conformal window, this theory is supposed to flow to an interesting non-trivial fixed point in the infrared where you have a superconformal field theory. And in this range, let's say there is a dual description in terms of another supersymmetric QCD. This time the rank is an F minus NC. And in addition, you have some singlets that are coupled to the mesons of the dual theory. So that's, of course, is a fantastic result, and it has lots of implication and has triggered a great interest. And since the discovery of, the proposal of the first infrared dualities in the mid-90s, a plethora of dualities of this type have been proposed. Okay, so different gauge groups, different type of matter content, really a lot of work has been done in this direction. So how do you, test a duality? Of course, this is a statement about the infrared where gauge theory tend to be strongly coupled. You cannot do perturbation theory, so you need to resort to some non-perturbative tests. So people have been mostly resorting in anomaly matching, so Toft anomaly matching, or try to establish a map of operator. Much progress came recently thanks to the development of the technology of the superconformal index. So this is basically a Witten index, refined with some fugacities. This object is an RG invariant, so you can calculate this quantity with the UV data of your theory, and it characterizes completely the physics at the infrared fixed point. So if you have a proposal for two theory to be dual, you can test it just matching superconformal index. And in general, the business of matching this duality, this RG invariant partition function to establish the duality has opened, a new, if you want, field where people physicists have been talking to mathematicians working mostly with special functions and which develop exact identities for corresponding to dualities. And so there has been, new results in the business of infrared dualities thanks to the work of mathematicians that they have developed some mathematical identities that really express the match of the RG invariant partition functions for gauge theories. Of course, please. Yes, sure. Sorry, where are we? Fantastic. So, yeah, I'm talking about mostly D equal 4 and 3. So in 5 dimensions, you have what you would call UV duality. So it is known that there are some gauge theory that are deformation of some UV fixed point. And then it's a bit different. It depends on the dimension of the gauge coupling. So here you flow to fixed point going down to the infrared. Then the physics is a bit different. Of course, it's very interesting also duality in higher dimensions, but the discussion for today is D equal 4 and below. Fixed, yeah, so this conformal window, it's the what Cyber, so QCD, ordinary QCD non-supersymmetric, it's known to have an infrared fixed point just below this number, 3 and C, which is where the beta function flips sign. That's the Banzhaf fixed point. At this point, you can convince yourself that the beta function has a 0. Then question is that, is this fixed point stable? And if you start decreasing the number of flavor, how long this fixed point exists. And then you need to figure out where the window closes. So to establish where the window closes, the argument of Seiberg is that you look at your operators, and what happens at this point, the mesons hit the unit bound. So since you are flowing to a conformal point, you want all your operators to be heavier than the free fields. And this happens when you are at this point. So this is the intuition of how you construct a conformal window. So this is the range where you believe that there is a interacting fixed point in the infrared. It's a belief, okay? Then you support this with tests. Okay. If you go below, in this region you have various instances of confinement. You can have a smooth confinement without chiral symmetry breaking. You can have confinement with chiral symmetry breaking. You can have a runaway no vacua. So if you remove the number of flavors, you go all the way down to super young meals. So also this region is interesting and studied, but I'm just talking about this region. And this is work by Seiberg in the 90s. So indeed there is a lots of interesting work below the conformal window. Very good. So as I was saying, after the work of Seiberg, really people have proposed a large number of dualities, which today we are able to test with these indices. And so a question that various people are asking themselves, including myself, is that whether all these dualities are independent or they can be organized. Maybe there are some dualities that are more fundamental than others, and it makes sense to organize them. So I'm not at the stage of a classification, but what I want to do today is to just give you some ideas on how we are attacking the problem of deriving some dualities from other dualities with the idea of establishing whether there is going to be a fundamental set of dualities, or maybe they are not all independent. So the two technologies that I have been working on with my collaborators and also other group are the sequential deconfinement that I will only marginally mention, and the dualization algorithm. And I wanted to add some comments that the work of Seiberg was done in 4 dimensions, then people also proposed duality in lower dimensions, and what has also been realized, mostly starting with this work, although the intuition was there earlier on, is that the dualities in 3 dimensions can be derived from those in 4 dimensions. So there is a procedure to compactify theories in a circle, and as you do this compactification, some non-perturbative effect can appear, but by now we know how to handle them. And I think I can state today that I don't know any 3D supersymmetric duality that doesn't come from Seiberg duality. So there is, from Seiberg-like dualities in 4 dimensions. So it looks that 3D, it's a byproduct of 4 dimensions. And in addition, once you are in 3D supersymmetric dualities, you can start, for example, integrating out matter, and you land on level rank dualities for topological quantum field theory. And again, I think, although maybe I missed something, that all the rank level dualities that we know for 3-dimensional TQFTs can also be traced back to Seiberg-like dualities in 4D through compactifications and giving mass to the matter fields. So that's the status. So it makes sense to really focus on in dualities in 4 dimension and try to establish whether all the dualities in lower dimension can be generated from 4D. So I'm talking about infrared dualities. There are also other type of dualities which I'm not talking about today. Mirror dualities are a different type, respect of the cyber duality. This is what was believed, and I will challenge this belief later on in my talk. So just briefly, I thought that it was good to have an idea what is this technology of the sequential deconfinement. So this is a technique that is applied to theories where the matter doesn't come in fundamental representation, but you have matter also in tensor representation, like adjoint, antisymmetric matter. And for this type of theories, dualities are known, which are not cyber dualities, cyber-like dualities, because the cyber duality, you only have matter in the fundamental, but dualities were proposed. And with this technology, the sequential deconfinement that builds on early ideas from the 60s, the idea is that you can derive these dualities assuming only dualities for theories with fundamental matter. So I'm going to give you an example just to give you the flavor of the story. So let me set up some notation. So this is my starting point. Is a theory with a single gauge node, which I represent with a circle. In this case, is a USP, is a symplectic gauge group node, and there are 3 doublets, so 6 fundamental chirals anyway. So. And then there is a field, which is the main character, which is in the antisymmetric representation. So this theory was studied together with other theories in the 90s, and this theory was conjectured to be dual to a theory with no gauge, so a Vezzumino model with 15N chiral fields. So this is a result that goes back to the 96. So here I set up a recursion to prove this duality, assuming only dualities for theory with matter in the symmetric representation. So it starts by considering an auxiliary theory. Now we have 2 gauge nodes. One has a lower rank. Now, in this highlighted orange rank, I apply a cyber-like duality locally. You see, I have just a theory with only links attached to them, no arcs, so there is no matter in tensor representation. So here I can apply one of the known cyber-like duality. In this case, it's interligator-Puyo duality. And the amount of flavor is such that when you apply the duality to this node, this gauge node confines, and the singlets of the dual theory reconstruct the antisymmetric of the original theory. So if you dualize this node, you go back to the original theory. On the other hand, if you dualize the yellow node, the fact is that now this node confines. So you cut this node, and you reconstruct actually the antisymmetric on the first node in a theory that it has a lower rank. And in the process, you produce some amount of singlets. So this, you can build an iteration. Each time you can go to an auxiliary quiver and apply these moves, and each time you knock down the rank and you produce some singlets. For example, this is an intermediate step. After K step, you are knocked down the rank by K unit, and you have produced 15K singlets. So if you iterate n times, you completely kill the gauge group, and you arrive at the expected dual, which is a Vezzumino model. Okay. The argument in the 96 were usual operator map, anomaly matching. That's it. This is actually, they filled a table, which is, today we can confirm, of all possible S-confining duals. They just did an algebraic exercise, they wrote anomalies, and they saw how you can, exactly. So indeed, this is the group of people that in the 90s sat down and classify all the dualities, if you want, for theories with tensor matter, where you have gauge theory dual to Vezzumino model. So they are called S-confining. So it's just the dual degrees of freedom are just singlets interacting with a superpotential, no gauge. So all this table that they filled in the 90s, now we can prove with the technology of sequential deconfinement, variation of what I just showed you, that they can be derived only assuming cyber dualities. So cyber dualities for theory with fundamental matters are enough to prove all the other types of dualities of like classified in the 90s. There are many, many, many. Okay, I cannot even list all of them. Okay, then you can apply this technology in other situations, but I thought that I wanted to make 2 interesting comments. So this technology that I show you here in field theory what is interesting is that it appears in completely different context. So I told you that for gauge theories, you can write indices, superconformal indices. Well, mathematicians have proven identities for these indices. So the identity the mathematician proof is some rank n integral being evaluated to some to a product formula. So they call it an evaluation formula. So this is work of mathematicians like Spiridonov and Rines working on elliptic integrals. And if you actually look down and see how they prove their formulas, they do some trick like this. They just do it at the level of formulas, but they apply the same idea of going to an auxiliary frame, an auxiliary theory where you have now two integrals, one rank n and one rank n minus 1 integral, and they do manipulations. The same manipulation, interestingly, appears also if you look at some papers by Dotsenko and Fatev, where they were manipulating free fields correlators into DCFTs. They were doing this type of manipulation. In particular, this is actually the exact type of manipulation that appear in the construction of the derivation of the DOZZ 3-point function, starting from the free field representation. So you represent a 3-point function as a rank n integral over the screening charges, you do some manipulation, you get an evaluation formula, which is the DOZZ formula. So it is interesting that this type of technology is transversal, it has an avatar in different contexts, and so it is a promising approach to kind of break down more complicated duality in more fundamental bits. So at this point, I mean, one had gathered enough faith in the fact that most infrared duality seems related to or descends from cyber dualities in 4 dimensions, and then cascading down to 3 dimensions, taking various limits, you can generate all the known dualities. Something that appears completely isolated from this story is mirror duality in 3 dimensions. They have a completely different origin, so it seems to be a separate discussion. But in fact, I want to show you that, in fact, they are part of the same, can be put in the same story. So let me say something about 3D mirror dualities. Now we are talking about theories with 8 supercharges in 3 dimensions, and they enjoy, this type of theories, a duality which is called mirror duality. And in this type of dualities, you have copies of theories where the Higgs and the Coulomb branches are swapped. So this is the signature of a mirror duality. So the simplest example is that of the supersymmetric QED. So U1 theory with 1 hypermultiplet, which is conjectured to be dual to a free hypermultiplet. So this is the conjecture. And how people convince themselves about this statement is that in the QED in 3 dimensions, you have an operator which is the monopole operator. You have monopole operators. So those are operators that are charged under the topological symmetry that you have in 3 dimensions. Remember, in 3 dimensions, you have every billion gauge field can be dualized to a scalar, a dual scalar, and you can shift the scalar. So this gives you a U1 topological symmetry, and there are operators that carry this charge. These are the monopoles. So these are complicated non-local operators, but we have technologies to calculate the dimension of these operators. And in this work by Kapustin and collaborator, it was established that these monopole operators in the QED have exactly dimension a half. Now, a half is the dimension of a free field in 3 dimensions. So it makes sense that the monopoles being free in the dual theory are mapped to a free hypermultiplet. So this is the first evidence of mirror duality. So typically you map a topological, you map operators that parameterize the Coulomb branch that carry this topological symmetry to mesonic operators in the dual theory that parameterize the Higgs branch. Now, what is interesting is that already like in the end of the 90s, Kapustin and Strassler observed that if you focus just on abelian mirror symmetry, this can be explained with a piecewise approach, like doing a local dualization, which in the end is nothing but a functional Fourier transform. So the idea goes more like as follows. If you want to reinterpret this duality that I mentioned here of QED with one hyperdual to a free hyper, you can summarize this statement in this expression. So ZH here is the partition function of a free hyper as a function of a background gauge field. So you think you are minimally coupling your hypermultiplet to some gauge field, some background gauge field. So that's give you ZH as a function of this background gauge field. And this is the partition function of a free hyper. Now, if you want to instead consider QED, you want to make this field dynamical. So you integrate over V is the vector gauge field you integrate over. Now you may think, what is the kinetic term for the gauge field? We are assuming we are in the infrared, so the gauge coupling is massive, so this theory, I can drop F mu nu square over G square. G is going to infinity. So the only thing that I put here schematically is just the supersymmetrization of a BF coupling, so something like A mu, which is the dynamical gauge field, F hat nu rho, which is a background, another background gauge field. So you see, basically the statement is telling you that the partition function of the QED as a function of the background vector multiplet is nothing but the partition function of a hypermultiplet, or also its Fourier transform, because we want to think that this BF coupling is acting like a Fourier kernel. And then basically, after this observation, they realized, okay, if you have more complicated dualities, abelian, you can generate all of them using properties of Fourier transform. So you can do convolution, you can do inversion. So all the abelian mirror dualities can be demonstrated piecewise, assuming only these simple basic mirror dualities, which, by the way, it's nothing but a Seiberg duality. This statement here can be derived from Seiberg duality in Fourier by some reduction and some maybe flip of singlets. Anyway, I cannot explain this. It doesn't matter. But this simple mirror duality is also a Seiberg duality. Okay, so this is the situation for abelian mirror symmetry. So I can say, okay, I understand abelian mirror symmetry, assuming only basic mirror symmetry, which is in the end Seiberg, but what about non-abelian mirror dualities, which is very interesting, of course. Well, here the situation has proceeded a lot looking at geometric construction. So brain setups, there is the work of Anani Witten that realized this class of three-dimensional theory with 8 supercharges with D3 brains suspended between NS5 and D5. Now, this is a type 2B system, and as such, it has the SL2Z duality of string that is then descending to SL2Z type of duality in gauge theories, and S duality generator here is just what corresponds to mirror duality in 3 dimensions. So this type of construction through brain has allowed all the immense progress that has been done recently, well, since the mid-90s in understanding the physics of theory with 8 supercharges. And this is another story that I cannot even go through, but the knowledge of mirror dualities in 3 dimensions has been extremely beneficial to understand also theories in higher dimension, but still with 8 supercharges. But I think this has probably shifted a little bit the attention from the question that I was trying to answer, that is whether I can derive all the dualities assuming only Seiberg dualities. So in this situation here of non-abelian mirror dualities, the work has proceeded just using brain construction, and there was less field theoretic effort in explaining non-abelian dualities. Okay, so this is the question that I want to ask, whether also mirror dualities can be explained in terms of Seiberg dualities. Notice the different amount of supercharges. Seiberg dualities are for theory with 4 supercharges, mirror dualities are for theory with 8 supercharges. So Two recent results that I will try to summarize, mostly the second part, is that first of all, one can construct avatars of mirror pairs in 4 dimensions, so with different amount of supercharges, but enjoying dualities that are very reminiscent of 3D mirror dualities. So in this sense, you can think that mirror dualities in 3 dimensions can be obtained as a limit of some type of dualities in 4 dimensions for n equal 1 theories. And the second result, both the 3D and the 4D mirror dualities can be derived with a procedure which we call the local dualization algorithm, which, if you want, is morally a non-abelian generalization of the idea of Kapustin-Strassler of demonstrating mirror duality piecewise. So this dualization algorithm builds on some fundamental dualizations, and which are basically cyber dualization, and then gives you a procedure to construct the mirror dual of any non-abelian theory with 4 supercharges. Okay, so questions so far? Okay. So kind of switching gear, I need to introduce some tools that I need to set up this algorithm. So here I need to work with some theory, which is a little complicated, but it plays a crucial role, so I cannot avoid presenting it. So it's a quiver theory. We have various round nodes which represent symplectic gauge groups, so USP2, USP4, and so on and so forth. Then you have an antisymmetric at each node, and it is in a superpotential with bifundamental chiral to its left and right. These little crosses are just singlets that are coupled to the square of these diagonal legs, so we say they flip these diagonal mesons. Anyway, what is interesting in this theory is that it has 2 non-abelian global symmetries in the infrared. So it's the first time that I'm presenting this type of effect where the symmetry in the UV, so this is a quiver that you write using the data in the UV of your theory, you see a certain amount of global symmetry. In this square node, you visualize an USP2N non-abelian global symmetry, but then you see a set of USP2 or SU2 nodes, so you would expect SU2 to the N symmetry, but this symmetry in the infrared enhances to another copy of USP2N. So the statement is that this theory in the infrared has 2 sets of non-abelian symmetry, USP2NX and USP2NY. In addition, there are 2 abelian symmetries, and I will be using this compact notation with this wiggle line to represent this more complicated theory. So this theory, which is a theory now, we are talking about a 4-dimensional theory with 4 supercharges, as it should be manifest from the way it is drawn, is actually invariant if you swap the 2 USP2N global symmetries and the operator carrying charge under these symmetries. And this feature, it's a self-mirror property. So this is the first example of a theory in 4 dimensions that enjoys a duality which is mirror-like. So you swap 2 sets of operators that are charged under a manifest and an emergent symmetry. And well, the reason why we call it mirror duality is that we know that if you do the reduction to 3 dimensions and some deformation, you can land on the, if you want, theory that is well known to be self-mirror, is this TSUN theory, which I will comment on in a moment, which is one of the prototypical example of self-mirror theory in 3 dimensions. So why I'm emphasizing so much this theory, this is going to be the key element in the algorithm, and the reason, I mean, the history of how we got to this theory is quite convoluted, but anyway, we discovered this theory while studying string compactifications, and at the same time, for different reasons, we also realized that this theory, if you look at the superconformal index of this theory, it is something that is studied a lot in the math literature, especially by this Eric Rines, has developed lots of work on the properties of this theory. Well, it is constructed with interpolation functions, which are a sort of a generalization of Macdonald polynomial. So it satisfies some equations, some difference equation, which generalize in some sense Macdonald. Although I cannot tell you why it's so interesting for Rines to study them. But we are very pleased that he has developed lots of stuff. Yes, absolutely. But if he has, of course, if you write the index for this theory, this is a horrendous nested integral for which he proves all the identities. Like these self-mirror properties for him is an exact identity, which is super non-trivial. Okay, so here is just, I wanted to make a table. So this is the theory that I just introduced. Is our four-dimensional mother theory. Everything is going to descend from this theory. There are various limits where you go to 3 dimensions. You have this intermediate theory. I don't want to spend too much time discussing it. I represent it with a double dash line. It's also is a theory which in a sense is self-mirror because you have 2 sets of non-abelian symmetries that are swapped under this duality. Now the non-abelian symmetries are of U and type. And a further deformation takes you down to this quiver theory that maybe is more familiar, is the TSUN or FTSUN quiver theory proposed by Gaiotto Witten. So here the ranks are U1, U2, and so on and so forth. And also this theory is self-mirror, and it has a UN and another UN symmetry. One of the UN is an enhanced topological symmetry. Okay, so there are various nice properties that you can prove for this mother theory, this wiggle line theory, which for me is going to play the role of the S-duality wall, and I will explain why it's an S-wall. One property that is proven by, well, it's listed in the work of Rines, but we recently have approved that is going to appear that is also descending from cyber-like duality, or more precisely intelligator Puyo duality, is the fact that if you glue 2 of these S-wall theories together with one doublet, you get a single S-wall. This is a sort of a star triangle property, or how it is named by Rines as a braid move. Interestingly, in a certain limit, it becomes a non-cyber duality if you put n equal to 1. Otherwise, it's of course a very non-trivial identity. This is instead another property that I don't think it was known to Rines, but we prove it. If you glue 2 of these walls together, you get a delta identity, a delta distribution. So this is something that you can check at the level of the index. It is a quite nasty thing to prove, but you can convince yourself that gluing 2 of these theories, you get an identity wall that identifies this global symmetry with this other global symmetry. So it's like what we call the identity wall. If you want to have just an idea, for n equal to 1, so you have SU2 with 4 chirals. This is a theory that Seiberg studied, and it is a theory that is known to have the 4 moduli space and chiral symmetry breaking. And it means that at the quantum level, there is a quantum superpotential that is telling us that if you that some of the operators, some of the means on acquire a VEV, a quantum vacuum expectation value. So if you try to gauge some part of the global symmetry, this VEV that appears in the infrared produces some Higgsing. So you cannot really gauge any of this global symmetry. It means that there is some less symmetry, and there is a delta function identifying the gauge, this flavor symmetries. Actually, this observation that the index of this theory is a distribution was already done by a mathematician, Spiridonov and Vartanov, who actually is a physicist. Anyway, so this is a generalization, is a non-trivial property. If you glue two of these S-walls, you get an identity. And this is also something that in perspective we want, because being an S-wall, you want it to satisfy some SL2Z relations, or actually what we will have is a PSL2Z relation. So we will interpret this property as S squared equal to 1, whereas this star triangle property is going to be interpreted as STS equal to TST, where T generator is going to correspond to a flavor. But I don't think I will have time to go through the SL2Z story, so we'll just focus on S story. Yes? Okay, I mean, I can give you some idea of the proof. Maybe I can explain the proof later, but the idea is that basically you take this result for granted, so this can be proven. So the way you see this is basically you look at the index of this theory, and you notice that naively the index is 0 because there are some zeros appearing. However, if you look carefully at the remaining fugacities, something happens when some of the fugacity collide. And then basically the support of the index is only at the special points, and it behaves as this delta distribution. So if you evaluate, if you integrate the index with a test function, it's like delta times the test function evaluated at points where the global symmetries are identified. Yes, yes. And so this is the basic idea, and then here you have to work a lot, but there is some procedure to basically break down this theory to n copies of this theory, in a sense. I can give you, in the paper we have this demonstration, is in this paper. Okay, so last thing before going through the idea of the algorithm, just to tell you which theories I'm going to focus on. So in 3 dimensions, the type of theory that you want to consider are the so-called linear quivers. So you have a bunch of UN gauge node. For every node, you have possibly some matter in the fundamental representation. Each node has an adjoint. So these are the theories that are realized on the D3 brane stretching between D5 and S5. And these theories here, where they have basically exactly the same structure, where you have now USP2N symmetry, and in addition, you have this so structure is the 4D version of the 3D mirror theories that we develop. So these are the two types of the two families of theories for which we designed originally the algorithm. So this is basically all linear quiver theory you can do in 3 dimensions with 8 supercharges, and here is the 4D version. So what is the idea of the algorithm? Well, the idea is very stupid, actually. So as I mentioned already several times, these 3D theories with the supercharges can be engineered with D3 brane stretching between NS5. And S-duality acts by, on the NS5 by dualizing each 5 branes. So what you do, you send an NS5 into a D5 and a D5 into an NS5. This is the action of S-duality on the brane setup. And not necessarily you want to do it simultaneously over all the nodes of your theory. You can So you not necessarily want to dualize all your 5 brains, you can do it locally. So you can go locally and dualize an NS5 brain, but at the price of creating an S-duality wall to its left and to its right. So you can do this local action on your brain setup, acting with the S-duality wall, and in principle you can do it with any other elements of SL2Z. Now, this S-duality wall has been identified with a gauge theory. It's this TSUN gauge theory that I flashed before, so it has a field theory realization, at least the wall. So what we wanted to do is to give a physics, a QFT realization of this operation that you do at the level of the brain. So we wanted to understand in field theory what is this operation of dualizing an NS5 into a D5. And intuitively, when you read the brain setup, when you have an NS5, you think of a bifundamental field. And when you have a D5, you think of a fundamental field. So what we are trying to do is really to find some basic duality move that dualize fundamental fields into bifundamental fields and vice versa. So that's the idea of the algorithm. The algorithm then is built on a set of basic duality moves that we define in field theory. And these moves are genuine infrared dualities that can be derived by Seiberg-like dualities. So connecting to the theme that I was discussing at the beginning, so our building block dualities will be basically something that I prove in terms of Seiberg duality. And then I have this algorithm to dualize any theory with 8 supercharges piecewise and to construct the dual. So this is the idea. I mean, I have my QFT that is associated to a brain setup. So this crosses corresponds to D5. The lines are NS5. So I see some bifundamental matter connecting different gauge nodes corresponding to NS5, and I have this square corresponding to N5 brains. So I can break down the theory as in terms of what I call QFT building block. So I have bifundamentals and I have fundamentals associated to NS5 stretching between different number of D3s and D5 stretching between different numbers of D3s. And here upstairs I have the same story, just I'm cutting into QFT blocks our 4-dimensional theories. Now a bifundamental is actually a triangle because I have this structure, but I can chop it. This chopping operation simply means freeze the gauge group, and then I will gauge it back after dualization. Then I have the operation, which is really the dualization. So the main dualization basic duality moves are these two. One corresponds to the dualization of a 0-1 brain, so a D5. Here I have a fundamental sandwich between two S-walls. Remember, for me, these wiggle lines or dash line corresponds to S-walls in different dimensions. So if I dualize a flavor sandwich between two S-walls, I get a bifundamental. So this is the field theory analog of this property that I have at the level of the brain. So a 0-1 brain sandwich between two S-walls is dualized into a 1-0 brain. So flavor acted on the left and on the right by two S-walls becomes a bifundamental. Okay, so let me stress again, these are Seiberg-like duality. In the end, I claim that this side is equal to this side because the infrared, they go to the same fixed point, and I can prove this in various ways. I can test indices, I can map operator, and I can prove these iterating Seiberg dualities. So these basic moves are the vanilla Seiberg dualities applied in a non-trivial way. So now, this is the algorithm. So the algorithm consists of 4 steps. In the first step, I give you a quiver theory and you chop it into blocks. So you engage the gauge nodes and you isolate fundamentals and bifundamentals. You dualize each block using this set of rules. So whenever you have a bifundamental, you replace it with a fundamental sandwich between two S-wall, depending on whether you are in 4D or 3D. This is how they look. And whenever you have isolated a fundamental block, you dualize into a bifundamental sandwich between two S-wall. Then, after doing this local dualization, you glue back your theory. And what happens is that at this point, you produce some identity wall. You will have colliding S-wall. This gives identity, the identity property that I showed you before. And in the last step, which actually is the trickiest step, you need to sit down for the moment and study the theory that you arrive, because some of the operator in your theory may have acquired some vacuum expectation value. So in the very last step, you are supposed to study the RG flow that is triggered by this VEV, and this flow takes you to the mirror of the original theory. So that's the idea of the algorithm. You can automatize this. We're trying. Maybe eventually we'll have a code doing that. Otherwise, you can call any of us and we can, implement the algorithm for your favorite theory. So here is an example. I'm trying to work out the mirror of a QCD in 4 dimensions. So the 4-dimensional version carries this triangle structure. I reintroduced some 0 nodes so to visualize that I have 2 triangles and a bunch of fundamental blocks. So that's my original theory. That's the theory that is cut into blocks. You see I have 2 red triangle blocks and a bunch of blue flavor blocks. Then I dualize, so now each triangle is replaced by flavor sandwich between 2 S-wall, so this one and this one. And then I have each flavor is dualized into triangle sandwich between 2 S-walls. Now you see, here I have colliding S-walls. Whenever I have colliding S-walls, I have identity. So I implement these identities, and I'm already in the next step of the algorithm, so I reach this theory. Now this theory is a theory where I drew here in blue some leg that is carrying some expectation value. This is something that we see from the charge, because the algorithm gives you the charges of all these fields, and by inspection you notice that some of these fields, they have charges that are compatible with some expectation value. So you are supposed to study the effect of this expectation value. At the first step, what happens is that the expectation value Hickses down this OSP2N gauge group down to a OSP2, and similarly here, so become a 2. And then you notice that again, there is some VEV going on, and this Hicksing wants to propagate. So you propagate until you extinguish completely all the vacuum expectation value that you have in your theory, and this is by definition is the mirror dual frame. So here is the mirror dual frame in 4 dimensions, which is the expected dual of this theory, and this is the mirror dual in 3 dimensions. I don't know if somebody is more familiar. This is the known mirror dual of QCD in 3 dimensions, where you reproduce these 2 tails, and then there is a plateau, and there is some flavor in here. So this story is to say that we have demonstrated that this duality, which is mirror duality in the non-abelian case, is a non-trivial consequence of Seiberg duality, which is the key, the basis of the dualization algorithm. And then you can dualize any theory proceeding locally with this dualization algorithm. So I don't think I will have time, so I will just conclude saying what else can we do. So this is just to rederive known results. So mirror of non-abelian theory were known with 8 supercharges. So our algorithm is deriving them purely field theoretically without resorting to brain construction. We can run the algorithm for other generators of SL2Z group. So I mentioned only the action of the S generator, but of course we can do any other SL2Z duality locally, and all of them can be ultimately generated only assuming Seiberg-like dualities. Something that I don't have time to talk about, but I think is quite interesting, is that the algorithm can be run also for the so-called bad theories. So these are theories which are a bit tricky because they are known to have operators that are below the unit bound. And so their dynamic is very intricate, and people have been trying to explain what happens in the infrared to these theories. And we're about to put out 2 papers where we discuss the physics of these bad theories using using our algorithm. And last thing that I wanted to mention, maybe in 5 minutes, is that the algorithm can be extended also to theories with less than 8 supercharges. So we can try to go to mirror dual of theories with 4 supercharges in 3 dimensions. And so I wanted to say something about maybe this. So, so far the algorithm that I was discussing uses a basic duality move, which, as I said, dualizes a flavor sandwich between 2 S-wall we are here in 3 dimensions, into an ordinary bifundamental. So that's what we can say it's an n equal 4 duality move. In particular, here, giving a little bit more details, this adjoint here, I'm using an n equal 2 language for n equal 4 case. So this adjoint is actually coupled to this chiral. So you have a term like this in the superpotential. So this is the feature, if you want, of an n equal 4 theory. You have a joint in a superpotential. And so the question is that how you generalize this move to the situation where this adjoint field is not coupled to the flavors. So you have a more general type of flavor. Well, we have a generalization of this dualization where the bifundamental is replaced by an object, which is this double dash line, which is one of these complicated theories that appear at a certain point, but it doesn't really matter what it is, but it is here you have just a bifundamental, here you have a theory, a non-trivial theory that has still UN times UN symmetry, but it has a non-trivial structure. So the claim is that if I want to construct mirror of theories with 4 supercharges, I should use as a basic move, instead of this move, this generalization. So here is a run of the algorithm for the n equal 2 SQCD with an adjoint and no superpotential. So this theory, now the superpotential is 0, so you have chiral field of in the fundamental, and then the fundamental, they are rotating as independent SUKs. So you have more flavor symmetry, and people have been puzzled for a long time how to realize mirrors for this type of theories. And the proposal is that if you run the algorithm, the mirror dual of this theory is this quiver where you replace bifundamental fields with this generalized object, this generalized bifundamental fields, which is this double dash line theory. Now, this proposal passes all the checks. So first of all, it's a constructive proof. So you dualize this theory into this theory. So by construction, they are supposed to be dual. But you can map all the operators, of course, all the global symmetries. In the past, there were proposals for what is the mirror dual of this theory, but they always had a mismatch of the global symmetry. So the key point is here is that you want to insert this generalized bifundamental that carries some flavor symmetry that is contributing to this infrared symmetry. So this, I think, it's interesting because it's telling us, it's giving us a proposal on how to study brain setup with D5 and NS5 prime, or NS5 prime and D5. So typically, I mean, when you study brain setup with less than 8 supercharges, things are less clear, and indeed people have always struggle to find mirror pairs with enough, with the correct amount of symmetries. So our proposal is that if you are in a n equal 2 brane setup, you want to replace bifundamental with this generalized object. So this is the proposal we are putting forward, and of course we don't know really why is that from the perspective of the branes, but this is what field theory is really telling us. So we are working on this. Okay, so this is what I've been telling you. The question that is still to be answered is that whether all the infrared dualities, including mirror dualities, can be derived by cyber-like, in terms of cyber-like dualities, and whether there is something that doesn't follow this pattern. Can we find some 3D duality that doesn't have a 4D uplift, or can we find any 4D duality that cannot be demonstrated in terms of cyber duality? And of course, what about non-supersymmetric dualities? We know many non-SUSY dualities that are intuitively, well, more than intuitively, are inspired by supersymmetric dualities, and I think it's interesting to try to see also pattern relating non-supersymmetric dualities among each other, and also in the same type of organization as we see in the supersymmetric case. Okay, I stop here. Thank you. So for example, in 3D non-supersymmetric dualities like bosonization, fermionization, they seem to follow from like mirror dualities, assuming that when you do the SUSY breaking, you don't do phase transition, you can recover mirror, the bosonization from mirror in 3D. Yeah, you can integrate, say, out the fermions on one side, you get the only boson on the, assuming that nothing strange happens. Let's say if you already know where you want to, and there are no phase transitions, so that the fixed point is still there if you break SUSY. I mean, there are proposals, Karch-Tong, they have derived these non-SUSY dualities from, like, yeah. And also, I mean, this type of non-SUSY dualities are like other types of non-SUSY dualities. They're like intermediate between rank level and Givion-Kutazov dualities. So n equal to Givion-Kutazov are for theories with Chern-Simons coupling. Of course, if you integrate out all the matter, you land on the rank level. And in between, there should be theories with less, like n equal 1 in 3D or 0 supersymmetry. And Givion-Kutazov are all derived, this is super solid from Seiberg in 4D. So you go down from 4D to 3D, you do some deformation, you get all the Givion-Kutazov. Then if you remove all the matter, you get all the rank level. If you can stay a little bit in between, leaving some matter but no SUSY, maybe you can generate all the non-SUSY, maybe. Here?
So what is the mathematical statement behind this quality?
Okay, so mathematically, what I can, the most mathematical thing that I can say is that I can write an index of this theory. So of, a nested integral on this side, a nested integral on this side, they are equal. So the superconformal index can be written using only the UV data of the theory, so the Lagrangian. If you give me the Lagrangian of this theory, which I can write, but it's long, I can write an index, sort of a refined Witten index for this theory. I can write the refined index for this theory, and they are equal mathematically, like as a function. No, they're not infinite dimensional integrals. They are, no, they are matrix integrals. So I mean, this is like nested integral, but more or less you have order of n integration. So they are finite dimensional integrals. So no, this is, I mean, totally under control. No. But yeah, so you can basically for all what I'm saying with drawing, we have matrix integral identities.
These are three persons who you associate.
Exactly. Yeah. So yeah. So this quiver here, if you write the index of this quiver theory, which is a nested integral, this is what you find, for example, in the work of this guy. He writes this from a completely different perspective, but it's actually the same function. And so at this point, when you have a matrix integral, you do your favorite thing to check dualities. You can expand, they can prove things exactly. So mathematically, things are under control because yeah. So all what I've been doing here with drawing, we actually do with horrendous integrals.